This problem here is asking us about the overall stability of a structure, so that's just what I was just kind of talking about with the little models there. Something very similar. We've got some kind of steel truss here. The centre of gravity won't be in the middle of this. It's kind of a triangular shape. But anyway, the question has given us where the centre of gravity is. It's 10 metres from the supports at the foundation here. This is a gravity foundation. And so they're just using the weight of this concrete block to make sure that this cantilevered truss doesn't fall over. And so we've got a 3 metre wide cantilevered walkway. It doesn't really matter the width, I don't think. It's constructed over a river cliff as shown in the diagram here. So we've got the river cliff here. The walkway is supported by a mass concrete block, so that just means it's a concrete block without any reinforcement in it. Must have a little bit, otherwise you couldn't connect it to it. But mass concrete block, which is also 3 metres wide. The total weight of the steel cantilever is 200 kilonewtons. So it's given us the weight of this cantilever. Hasn't given us the weight of the block though, we'll notice, but we've got the volume. So it's 3 metres wide and then it's 6 metres by 6 metres. Is the structure stable? So the whole point in this, so you've got to think about where would this thing rotate. I've already marked it on, but if this was going to fall over, it would rotate around this point, just the same as the blocks we were looking at earlier. And so what we're going to do is we're going to look at the moments from these dead loads, they're called, from the gravity loads. We're going to find the weights from these dead loads, and we're going to figure out what's the restoring moment. So that's the moment due to this, because it's going to be acting downwards. Got a lever arm here, so it's going to be a restoring moment. Let me just draw it on so you can see what I'm talking about. So this weight of the block is going to be a restoring moment. This weight here, it's going to tend to rotate the structure the other way, so it's going to be an overturning moment. And then we're just going to make sure this restoring moment is greater than the overturning moment, then we'll know that this thing is stable. So it's not going to fall over. So let's work through the calculations. First, I'll just calculate the volume of the block. And so you should be memorizing that the unit weight, so we're wanting weights here, not masses. We want the weights so we can figure out the forces. And so the unit weight, or the weight of a structure, is just given by weight is equal to unit weight times volume. So let's see what we know. We know that the unit weight of concrete is 24 kilonewtons per metre cubed. Just one of these things you need to learn. The volume is just equal to, should I write the formula? Probably not, but length times breadth times height. It's just a cuboid, that thing. It's going to be 6 times 6 times 3, which is going to be 36 times 3, 90, 108. 36 times 3. Yep. So it's going to be 108 cubic meters is the volume. So therefore the weight is equal to 24 times 108. That one I'm not going to try and do in my head. 24 times 108. Just a second, my calculator's being silly. 2592 kilonewtons. 2592 kilonewtons is the weight of the concrete block. We already know, does that sound about right? I think it is. 6 times 6 times 3, 6 times 6 times 3, that looks about right. Yep. So now we're going to have to figure out, I might just move this 6 meter, I might just delete that 6 meters, we know that now. So what have we got here? We've got a weight here. And we've got a lever arm. So because the centroid, we can just figure out it's just a simple shape, it's just a rectangle. You might get more complicated problems where you have to actually calculate where the centre of gravity is, like this might not be a rectangle, and so you might have to calculate where that is. But in this case, I'm just trying to illustrate the idea of overturning. So that is going to be, let's just call that F1, and it's going to be equal to the weight, which is 2592 kilonewtons. This distance here is the lever arm, perpendicular distance to the point of rotation. So that's going to be D1. Then we're going to have over here, we're going to have a force downwards, which is 200 kilonewtons, told us in the question. So 200 kilonewtons, I'm not drawing anything to scale here. 200 kilonewtons. And, oh, just call that F2, sorry. Just writing down what I'm doing so you can see and do the calcs. F2. and the distance, perpendicular distance to the point of rotation so that we can calculate the moment. That's going to be d2. So let's calculate this one's very simple. There's only one restoring moment, one overturning moment. You could be more than one. You could have, well, for here you might have the weight of this, but you might have something on it as well. So you'd have restoring moment from the structure itself. Oh, sorry, you'd have an overturning moment from the structure itself. Then you might have an overturning moment from some load that's on top of that. We're ignoring this little fella here. But given that this is 200 kilonewtons, so this weighs 20 tons, the weight of this wee fella is not going to make much difference whatsoever. Okay, so what we're going to do now is just figure out overturning and restoring moments. So, oops, I just need to escape this. So overturning moment first, say. From F1, it's just equal to, sorry, it's F2 that's got the overturning moment, so from F2. So let's just write that out. M2 is equal to force times lever arm, which is equal to 200 times the lever arm is 10 meters, gave us that. So that is 2,000 kilonewton meters. Okay, restoring moment. From F1, okay, so it's tending to make this stale, it's tending to make it sit back down. So M1, I should just put the direction on this, so it's that way, is equal to W times, so it's, well, same thing. So it's F1 times D1, which is just equal to W times D1, which is equal to 2,592, and the position of this will be smack bang in the center, so it's times 3, which is equal to 2,592 times 3, 7776 kilonewton meters. Did it ask us for anything else? Not really. And that is going that way, so it's a restoring moment. So we've got really just at the answer. So you can see the restoring moment is much larger than the overturning moment. Why would that be the case? Well, because they'll want to allow for the weight of people on top of this and so on. And you want a factor of safety. Usually on overturning, you've got a factor of safety of 2. So you want the restoring moment to be twice the overturning moment. Not always, sometimes a little bit less, but there's a rule of thumb. And so therefore we know overturning moment is greater than, overturning moment is less than the restoring moment. So overturning moment is less than restoring moment. Or you could write it the other way around. Restoring moment is greater than the overturning moment. Therefore, structure is stable. And that should answer the question. So this was a very simple problem. In reality, it might be a bit more complex because you need to figure out centers of gravities and weights for composite objects. But in this case, just illustrating the idea. So you just make sure the moment that's making it sit down is bigger than the moment that's trying to turn it over, and you're all good.